about recent development in the study of metastable interacting particle systems. This is a joint work with Sanu Kim, who is the moderator of the current section, and Claudio Landim and Diego Marcondes. Okay, today I'm going to introduce two famous interacting particle systems known as the gel-range process and the inclusion process. Let me start with the supercritical one and the supercritical gel-range process, and then proceed to critical case in the later section. So let's just start from this one. So I'll introduce the model gel-range process here. The gel-range process is an interacting system of n particles, where each particle behaves as a random walk on a certain fixed finite set S with a jump rate R given here. And so that we can represent this gel-range process as dynamics on this space Hn, where here eta denotes the configuration and each coordinate eta x denotes the number of particles at site x. So eta Hn consists of configuration with n particles here. So the dynamics of gel-range process is given by this form of generator, and with this generator, which implies that a particle at site x jump to site y with rate g at x rxy, where g is a function satisfying this kind of asymptotic relation with some parameter alpha given here, which is important in our discussion. So in this talk, this kind of precise formula is never important. You can neglect it if you are not able to catch the meaning immediately. So I'll explain it with a picture or something like that. So now let's look at this rate more closely, the meaning of this rate. Since the function g here is decreasing in n, we can observe that if you have more particle here, more particle at x, then it is less likely to jump to site y. This means that the particles are sticky. Because you have more particle, then you less likely to jump. So you have a sticky interaction thanks to this form of generator. So here we can observe a phase transition because of this competition between sticky interaction and diffusive behavior of particles. So if alpha is less than 1, this is instead of this sticky interaction, the diffusivity of particle dominate entire system, so we observe diffusive behavior. However, alpha is greater than or equal to 1, then this sticky interaction overwhelms the entire system, and we observe a phenomenon known as the condensation of particles. Let me explain this condensation of particles in more detail. We denote by m the invariant measure for the underlying random walk, which is denoted by x dot. So this is the underlying random walk given here with the rate r. And then with this m, we can write down invariant measure of gel-range process as mu n in this way. As I mentioned before, this formula is not important. But the important thing that you have to remember is that we can write down the invariant measure in an explicit manner. Okay. Now I introduce 3 important notations which will be frequently used in the remaining part of our presentation. So the set S star denotes the set of sites at which the maximum of this invariant measure is achieved. And EX denotes a set of configuration such that the number of particles at site X exceed n minus ln, where ln diverges to infinity but slower than n. So for example, you can take ln as log n or something like n to the 1/3 or something like that, any number. So for configuration belongs to EX, almost all the particles are condensed at the site X, right? Now we define the set E as union of EX, where union is taken over S star. So for configuration in eta, the particles are condensed at one side among the of the set S star here. So we say that we observe a condensation of particles at site S star if this event has a measure close to 1 under this invariant measure of zero range process. So when you sample the configuration according to the zero range process, then particles will be condensed at one site of S star with dominating probability. Such a condensation of particles can be proven for zero range process easily with this explicit expression. For alpha greater than 1, you can find this asymptotic mass of this this set EX, and of course this implies this one because you sum over X, right? For alpha equal to exactly 1, then you have the same result, but you have to take ln as a number close to ln, close to n. So for example, you have to take ln as n divided by log n or something like that in order to this relation along with this relation. So this additional condition makes the critical case much harder than supercritical case, as we will see later. So in this section, we focus on this supercritical case. So we have a condensation for zero range process, which means that if you start from any configuration, then learn your zero range dynamics. Then what happens is that, as usual in Markov process, the distribution will converge to its invariant measure, so that, which means that you will observe a condensation of particle as time grows. So this condensation of particles happen in the time scale of n square, according to this work by Beltran, Hara, and Landim. And this is the first thing that you will observe. Now let's assume that you have this condensation of a particle at site X. This is locally stable in the sense because particles are sticky. So this is particles are sticky. So once you have this condensation, then this you will stay at this condensation for a long time. Indeed, for a time scale of n to the 1 plus alpha. So since alpha is greater than 1, this is longer than this one. So this is locally stable state. But in the end, because of the randomness of dynamics, you will observe that this the movement of this condensed site. This condensation will be modified, and another condensation is formed at the other site after the time of order n to the 1 plus alpha. So this is a typical metastable behavior because you have a locally stable state. So once you achieve this locally stable set, you will stay there for a long time. But in the end, you leave there to another locally stable set. And then you will do the same thing forever, right? So this is a typical metastable behavior. And for this region, we call EX as a metastable set or metastable valley. So our purpose in this business is to describe this metastable behavior in a rigorous manner. How to do that? We have to do this through this the so-called order process. Okay, this is to introduce order process. I prepared this picture. So this is a visualization of zero range process. So the zero range process starting from EX, which denotes the configuration most of whose particles are concentrated on site X. And then this is locally stable, as I mentioned before. So you stay here for a long time, but in the end, you make a transition to EY and stay here for a long time and make another transition and so forth. So to understand this transition jump behavior, you first define trace process, which is obtained by removing all the excursion outside of these metastable values. to simplify our computation. Then define order process as following. So you don't want to look at exact location where you are. You just want to look at which metastable set that you are belongs to. So define YNT as the index of metastable set at which your speeded up trace process belongs to. So theta n here is a speeding factor. We have to speed it up process because you will stay here for a long time, right? Otherwise, you will observe trivial behavior. You suitably speed up the process in order to see this transition. So by defining this object, you first speed up your process in order to see the jump within order 1 scale, and you just look at the index of value that you are staying. So this is a process on S star, which summarizes the metastable behavior of a zero range process. Because if the zero range process jumps from EX to EY, then this order process will jump to X to Y. So you can characterize the metastable behavior by proving the convergence of this order process to a certain Markov process, Markov chain on S star. So if you can show that this order process converges, or order process can be approximated by a certain Markov chain on S star under certain scale theta n, then you can say then the metastable transition happens in the scale theta n, and your metastable behavior, which is jumping among these metastable values, can be explained by this limiting Markov chain Y. Of course, you have to show that this excursion that we removed is negligible, and that can be verified by showing that you do not spend meaningful time outside of a valley. So this is easy to verify in most situations. So I will focus on part 1 in the remaining part of the lecture. Okay, now let me, before explaining how to prove this, let me first explain what this theta n and what this limiting Markov chain Y is. So define, as I mentioned before, this scale theta n is n to the 1 plus alpha. And Y, limiting Markov chain, is a Markov chain on S star with is expected to be a Markov chain on S star with a certain form of jump rate. Here I don't want to explain detail, but this CG here is a constant depending only on the function G used in the definition of zero range process. And M star is the maximum of the invariant measure of the underlying Landim. They are not important. Capacity, cap XY denotes the capacity between X and Y with respect to the underlying Landim. I don't want to explain the detail about this capacity, but the important thing to remember here is that this rate is proportional to this notion capacity here. Okay. Fortunately, this supercritical zero range process is now completely analyzed. Okay. Beltran and Landim shows answer these questions when the zero range process is reversible with respect to each invariant measure. And then in 2014, Landim showed the same thing for a certain special case of non-reversible case. And recently I solved this question for a general non-reversible zero range process for all supercritical case. In the paper, I explained the proof for alpha greater than 2, but it is easy to extend it to alpha greater than 1 as well. So now I will explain how we can show this, how we can answer this question 1 in particular. So the proof of this kind of convergence result of order process to a Markov chain is based on 2 ingredients. The first one is, first ingredient is the mixing inside the belly. So this estimate says that, okay, if you start from a metastable configuration in metastable set EX, then you hit the configuration zeta before reaching to other value. Here, this E minus EX denotes the set of the other values. So by showing this, you can say that you hit almost every point here before leaving this valley. And which implies that you forget the starting location when you leave this valley. So this provides an extremely strong sense of mixing for this metastable process. So metastable behavior consists of two ingredients. First, you mix your process inside the metastable set and then make transition. So this is the first step of a metastable behavior. The second one is the estimate of a so-called mean jump rate. As I mentioned before, you don't need to look at this in detail, but this is a certain weighted average of jump rate of trace process. Trace process is another Markov process, so you can define jump rate. So you can average jump rate. So this is average jump rate from set at EX to set EY. So if this conclusion here is correct, this mean jump rate will multiplied by zeta n because you speeded up the process by zeta n. So you multiply this mean jump rate by zeta n. This should converge to the rate of this limiting Markov chain. This should be true in the end. But in this case, so what Beltran and Landim showed is that if you are able to verify this strong mixing condition and this convergence of mean jump rate, then you can answer these two questions. That is what Beltran and Landim did. Of course, the first one is easy to verify as soon as it is true. The difficult part is part two. Now I'll prove how we can prove this part two, the remaining part. So in order to explain that, I have to introduce the notion known as capacity. So first we define equilibrium potential, which is a function whose value at configuration eta is defined by the probability that the zero range process starting from eta hit the set A before the set B. This is easy to define, and capacity is just defined as a Dirichlet form of this equilibrium potential, where Dirichlet form is defined as a standard way. Okay, capacity is easy to define, but hard to estimate in general. So how to estimate this mean jump rate, which is very complicated object? Okay, that is given in this theorem. You can express this mean jump rate in terms of capacities only. Even for non-reversible case, you have this annoying term, but this we observe that this annoying probability can be estimated by estimate of the capacity and the sector condition of the process. Of course, sector condition is satisfied for zero range process as well. So thus, summing up with this expression, we can reduce the mean estimate of mean jump rate to the estimate of capacity. That's the first step. Next, we have to estimate the capacity, but there is a standard way to do that. For example, you can represent capacity as a minimum of Dirichlet form over a certain class of a function. So this minimization problem says that by taking any function in this simple space, by taking any test function, and by computing the Dirichlet form of that function, you can immediately get the upper bound of capacity. In order to make this sharp estimate, you have to take a nice approximation of the optimizer of this variational problem, which is equilibrium potential. So by doing that, you can obtain sharp upper bound for capacity. For lower bound, you can use this Thomson principle, which express capacity as maximum of a certain quantity. So here I don't want to spend much time to explain the flow, but this is maximization over a space of divergence-free flow. Yeah, you can refer to these papers for the definition of flow structure, but I would like to stress here that, so you can do the same thing. You can take a test flow to get the upper bound of lower bound for capacity, right? If you take any test flow and computing this quantity, then you get the lower bound. The problem is that divergence free flow is very hard to construct in general. So that we, instead of this Thomson principle, we usually use Cauchy-Shubart type of argument for the reversible case. And that is the typical story for reversible case. It's relatively easy to estimate capacity so that we can estimate this mean jump rate. However, for non-reversible case, the story has been changed because we can again get express capacity as a minimum of certain quantity or maximum of certain quantity. So we can, in principle, do the same thing. The problem is that now we don't have, we have to confront to construct this divergence free flow. That has been carried out in my work with Claudio Landim, so that we constructed the divergence free flow to compute capacity and then compute the metastable behavior for certain model. However, constructing this divergence free flow is extremely complicated for many models, including zero range process. So I modified this methodology a little bit so that we allow a small divergence for this flow. And then using this slightly generalized method, I analyzed this non-reversible zero range process and answered the questions for zero range process. In recent work with my student Jungyang Lee, which will be posted to archive maybe next week, we found a nice way of estimating this capacity without using this test flow. We only use test function to estimate capacity. That is another method, and I believe that this is very nice one in the study of non-reversible process. Okay, this is the story for supercritical zero range process. And now I go to the critical case. So for critical case, I mentioned before the condensation happens if alpha given here is greater than or equal to 1, right? So now I focus on this critical case. So to explain this, I have to start by introducing this limiting Markov chain and the scale theta n. Recall that this scale is given by n to the 1 plus alpha for supercritical case, and limiting Markov chain satisfies its Markov chain with this form of jump rate. For critical case, it is conjectured that we still have the same form of Markov chain, but there will be an additional log n factor for the scale theta n. The appearance of this additional factor is coming from the fact that the metastable set here is much larger than supercritical case. So you stay there for a longer time scale. Okay, this conjecture has been verified recently in my work. If we assume that this underlying random walk is reversible, so that the zero range process is reversible, and moreover, this random walk has uniform invariant measure. So that since this is invariant measure, S star, which is the set of site with maximal mass, is just becomes S, the set S. So with these two assumptions, we verified this conjecture, but for general case, it's still open. I'll explain what's the difference for this critical case compared to the supercritical one. Recall these two main ingredients in the proof of supercritical case. And now I'll explain why we cannot have this strong mixing property which holds for supercritical case. So the reason is very simple. In this case, metastable valley defined as a configuration with n-ln particle at site x. Here we should take ln as n divided by log n or something like that. It should be very close to this number. Then if you count the number of configuration in this valley, then its order is ln to the s minus 1, which is much larger than theta n. Oh, theta n, which is a transition time for metastable your zero-range process, which means that you have much more configuration than your transition time, and each jump happens in the time of order 1. You cannot have this one because you cannot visit you just visit small portion of configuration inside your belly. Since this second estimate is based on this first one, you cannot expect the second one can help you as well. So we don't no longer have these two nice and standard ingredient in the study of metastability. So we have to replace them in other result, and we replace the first one with local spectral gap and certain attracting property. Let me explain why. So now we cannot expect this kind of strong notion of mixing. So we prove a slightly weaker notion of mixing than that one, and I'll explain them. So this is a visualization of metastable set EX. Okay, in this set, what we prove is following. You restrict your zero-range process on this set by excluding jump to the outside. Then for this, so you obtain zero-range process only on this set, right? Then you compute a spectral gap for this zero-range process. Then you can show that inverse of spectral gap is of order ln square, which is since ln is n divided by log n, this is much smaller than theta n, which is n squared times log n. Which means that since the inverse of spectral gap, which is also known as relaxation time, quantifies the mixing time of your process, your Markov restricted zero-range process in this set. Therefore, this relation implies that your zero-range process mixes in this set before reaching to another valley. And this is used in the identification of limit point of order process. I also would like to mention that this spectral gap as well as this restricted process are notions of reversible process, and hence we need the reversibility for this of the zero-range process for this step. So this is the first one. And in order to explain the second one, I define a slightly larger set than metastable set and more deeper part of this metastable set. And what I wanted to prove is the following. If you start from here in the set EX, then you want to prove that you hit this bottom before escaping from this larger set. So you always hit the bottom and go back, and you always hit the bottom and go back. So that with the dominating property, you take enough time to make a transition. That is what is required in order to show that your order process is tight. Of course, you want to show the convergence of order process, so you need the identification of limit point and tight. So you need both. So how to prove that? You prove that by constructing a superharmonic function on this region, satisfying this relation. So constructing this superharmonic function takes 20 pages of computation, and we use uniformity of invariant measure of the underlying random walk here. So you can possibly remove this uniformity assumption if you can show this by other means. So we successfully replace step 1 by these two ingredients. And now you have to replace step 2 as well, but and it is replaced with analysis of path communication. Because of the limit of the time, I decide not to go over detail, but I just want to explain essence of this method. The essence is the following. You can identify the limit point of order process by analyzing the solution of this Poisson equation. This does not require any reversibility or something like that. in the analysis, and it is very robust method. This has been developed by Fred Nezcano and his student O in 2018, and has been further developed and systemized in subsequent works listed here. In this critical gel range case, computation is more demanding than these previous results because we only have this weak notion of mixing. Previous work have this strong notion of mixing instead. So more demanding computation, but we can use this Poissonification approach to show, to identify the limit point so that we can prove this here. That is the story for critical case, which is entirely different to the supercritical case. Now let's proceed to the last topic, which is another process known as the inclusion process. So inclusion process is another one. So I'll use similar notation as before. So this is a system of n particles. Each particles are random walk on the fixed finite set S with the jump rate R. And inclusion process is defined as a dynamics on Hn with generator Ln acting on F in this manner, so that the particle at site X now jump to Y with this rate. Now I explain what is the meaning of this rate. The first term explains the diffusive behavior of particle. Because if there is no this red term, then the generator implies that generator only with this blue implies that your particles are independent and diffusivity is the end. So this is diffusive behavior. This explains the diffusive behavior of a particle with the diffusivity Dn. On the other hand, the second one explains the attracting interaction. To see this, let's look at this this picture again. This implies that if you have more particle here, then the jump from X to Y is activated, right? Its quantity becomes larger, which means that the particles located here attract this point, which means that particles are attracting each other. So if this diffusivity, Dn, goes to 0, then this attracting force dominates the system. And again, we observe condensation. I would like to stress that in the gel range case, we observe condensation of particle because particles are sticky. Here, condensation happens for different reasons, right? This happens because particles attract each other. Okay. Let me first explain reversible case, which is not that different to gel range case. In this case, we can write down invariant measure in this way, where gamma here denotes the gamma function that you know. And the metastable value here is slightly different in that it consists of only one configuration with the full condensations. And every particles are located at X, right? Yeah, under this condition. So you are expecting to see that every particles are condensed at one side in this under this inclusion dynamic. And what is that is the result obtained by Bianchi-Dommers and Giardina in this paper. They show that if inclusion process is reversible and the diffusivity Dn converges to 0 faster than 1/log n, then you observe a condensation of particles. Okay, since we have a condensation of particle, the next concern is the metastable behavior. That is also analyzed by the same paper. In this case, the scale is 1/dn. Scale for metastable transition is 1/dn. And with this speeded up by this factor, then the other process converges to y, where y is defined as the jump rate of y is just the jump rate of the underlying random walk. But the point is that this y is a process on S star, which is a subset of S. S star is a collection of sites with maximal mass, right? So this is a visualization. So here red points indicate the state site of S star, and black represent site of S minus S star. So this process is Y is a restriction of underlying landmark on the red side. So note that jumps are, there is no one-way jump because of reversibility. If you can jump from this side to this side, then you can do vice versa because reversibility. Okay. And the point is this: if you start from here, your condensation starts from here, then according to this result, you will stay at among these four sites. You just jumping around these four sites. If you start from here, then you just stay among these six sites. And if you start from here, then you will stay here forever in this time scale. What we can expect is that if you wait much more longer time, then you can observe a transition from this component to another component, right? If you wait much more time than this one. That is what is known as the second time scale. If you wait n divided by dn square, which is much larger than this one, then you can jump from a component to another component whose graph distance is 2. So you can jump from here to here, and you can jump from here to here, but you will not jump from here to here because graph distance is 3. So the proof for this appearance of a second scale, along with a very precise analysis, is carried out in the same paper when the graph is very simple of this form. Recently, Kim, who is the moderator of the current presentation, generalized this to any random, any general graph. Right? Okay, so this is the second scale. Now, if you wait even longer, then you can observe a jump from this blue component to another blue component, right? That is what happened in third time scale. So if you wait more, then we are able to jump among these two components, and Markov chain convergence has been verified only for special case at this paper. They assume that the graph is a simple line graph, and then they show the third time scale. So general third time scale is still an open question in this problem, even in the reversible case. Okay, this is the summarization for what has been done for reversible case. And now let's turn to the non-reversible inclusion process, which is the last topic. I will finish this within 5 minutes. Okay. So the main feature of this non-reversible inclusion process is that we cannot write down expression invariant measure in explicit manner. This is a huge problem because in all the previous models we can write down invariant measure, but in this case we cannot. This make a problem considerably harder than previous one. So let's define metastable value as before. But even condensation is now a non-trivial question. It is very hard to prove this because you don't have explicit formula. You just have to work with this generator to prove this. That is a very difficult mission. And even if you show this, it is very hard to characterize as cond, which is the set of site at which condensation really happens. In all the previous cases, this was S star. But in this non-reversible inclusion case, we expect that they are different. So what we did for this model is that we focus on the fact that not only this metastable value, but also energy landscape between these metastable values are quite simple. Based on this observation, we estimated a mean jump rate, estimate of mean jump rate using this observation regarding energy landscape. So this is interesting. So you say that this mean estimate of mean jump rate say that if you speed up your process by 1/n dn, then your stick condensed site move according to this rate, right? Which is defined in this way. So if AXY is a positive number, then AYX should be 0 if you look at this definition. So now this is one-way Markov chain. You can, so that you can visualize this Markov chain with rate A by using this arrow. You can, so if your condensation starting from here, then it will jump to either this side or this side in according to this G, the Markov chain G. So, okay, now let's define S0 as the recurrent state of this dynamic G, which is constructed according to this, using this A. Which means that if you start your condensation at this transient site, then you go to this site and this go to this site and you arrive to recurrent component and you stay here forever. The same for here. So that you can expect that condensed, you cannot have condensation at this site with respect to the invariant measure, because your condensed site must converge to either this component or this component. So you can expect that condensation happen in these red sites, and the limiting Markov chain is the restriction of this Markov chain G on this site, because you have this estimate of mean jump rate. However, to prove rigorous result, we assume that this Markov chain, limiting Markov chain, is irreducible, which means that these lead components are, there is only one lead component. Otherwise, we do not know which one of these two components are dominating the condensation. So we have to assume this in order to get rigorous result at this moment without explicit invariant measure. So what we showed is following. If we assume that condensation occurs for non-reversible inclusion process, then this set S0 is the set of site at which condensation happen. And we can furthermore find asymptotic mass of metastable set in terms of the unique invariant measure for this limiting Markov chain. You have a unique invariant measure as it is irreducible. If there are multiple components, then you don't have any idea about this in the limiting mass. And moreover, with this scale, as expected, the order process describing metastable behavior converges to this Y process. Okay, the last thing that, so this is complete analysis of metastable behavior when this has one irreducible component, the current component. But we still have to show that the condensation, condensation occurs. That is the difficult part. So there are two cases, two types of non-reversible inclusion processes for which we can show the condensation of particle. The first one is the case where the invariant measure of underlying random walk is uniform measure on S. For this case, you can just write down invariant measure explicitly, so there is no difficulty in showing condensation of particle. So the difficult part is the second one, which shows that in this work, we show that condensation occurs if all the rates are positive and dn decays to 0 sufficiently fast. Even with these too much assumptions on the jump rate, it is extremely complicated to show the condensation because we don't have explicit expression of the invariant measure. I would like to say that, so summing up, for these two cases, we can get this condensation and metastability result rigorously. And I would like to mention that this is the unique and first rigorous result in the study of non-reversible metastable process, where we don't have invariant measure expression, closed form formula for invariant measure. Okay, this is the last page, and yeah, this is end of presentation. Thanks for the organizer for providing this wonderful conference, and I hope that everyone here and your family or friends are perfectly safe against this COVID-19 virus. Thanks. Mm-hmm.